Welcome to today's paper reading. Today's paper is titled Quiet-STaR, Language Models Can Teach Themselves to Think Before Speaking. This paper was published on the AR14 preprint by Zelikman and colleagues from Stanford University and Not Bad AI Inc. The abstract highlights the importance of reasoning in written text, which is often implicit. For instance, reasoning can be seen in the unstated steps between the lines of a mathematical proof or in the underlying theory of mind during a conversation. The paper introduces Quiet-STaR, a model that generalizes the self-taught reasoner, STAR, by enabling language models to generate rationales at each token to explain future text, thereby improving their predictions. The authors address significant challenges such as the computational cost of generating continuations, the language model's initial inability to generate or use internal thoughts, and the need to predict beyond individual next tokens. They propose solutions including a token-wise parallel sampling algorithm and an extended teacher forcing technique. The results show that generated rationales disproportionately help in predicting difficult tokens and improve the model's ability to answer challenging questions directly. This approach leads to notable improvements in zero-shot performance on tasks like GSM-8K and Common Sense QA, without requiring fine-tuning on these tasks. The introduction highlights the importance of understanding the context behind text statements for a deeper comprehension. This is particularly relevant for language models, LMs, which have shown shallow understanding without reasoning in tasks like common sense reasoning and theorem proving. The self-taught reasoner STAR framework demonstrated that LMs can improve their reasoning abilities by training on question-answering datasets, but this approach is limited by the scope of curated datasets. Quiet-STaR extends this by training LMs on a large internet text corpus, allowing them to learn reasoning from diverse tasks. This approach leverages the LM's existing reasoning ability to generate rationales and uses a reinforcement-based reward system. The results show improved zero-shot reasoning abilities on tasks like Common Sense QA and GSM-8K. Figure 1 illustrates the Quiet-STaR algorithm, which involves three main steps: thinking, talking, and learning. In the thinking phase, thoughts are generated in parallel after every token in the text. During the talking phase, the model makes a mixture of next token predictions, some with the generated thoughts, and some without. Finally, in the learning phase, the model uses reinforce to enhance the likelihood of thoughts that aid in predicting future text, while discarding those that hinder this prediction. This process aims to improve the model's ability to generate rationales that explain future text, thereby enhancing its overall performance. Figure 2 presents the generalization results of the model trained with Quiet-STaR, focusing on its ability to directly answer reasoning-required problems. The left plot, A, illustrates the zero-shot accuracy on the GSM-8K dataset, while the right plot, B, shows the same metric for Common Sense QA, both without fine-tuning. The x-axis denotes training steps, and each line represents a different number of thinking tokens utilized during Quiet-STaR training. The y-axis quantifies the zero-shot direct accuracy on the respective datasets. Additionally, an inference-normalized version of this plot is included in Figure 6 for further analysis. In the realm of language models, several studies have focused on enhancing their reasoning capabilities. Rajani et al., 2019, showed that fine-tuning a pre-trained model to output reasoning traces before answering questions improved performance. Schwartz et al., 2020, demonstrated that with scaffolding, language models can generate chain-of-thought solutions. Nye et al., 2021, found that scratchpads required less scaffolding as models became more capable. Training language models to reason involves using mind reasoning traces or leveraging self-play techniques. Self-taught reasoner, Zelikman et al., 2022, iteratively trains models on their own reasoning to solve increasingly difficult problems. Metatokens, or function vectors, have been shown to optimize specific functions within neural networks. Prompt tuning, Lester et al., 2021, and context compression tokens, Mu et al., 2024, are examples of this approach, focusing on efficiency and downstream behavior control. In this work, the authors introduce an auxiliary rationale variable between each pair of observed tokens in a sequence. The goal is to optimize a language model with parameters theta to generate intermediate thoughts or rationales. This approach aims to maximize the expected log probability of the sequence given the initial tokens and the rationale. While in principle this does not provide an advantage over an optimal language model, extensive prior work has demonstrated practical benefits, particularly in reasoning tasks. These benefits are attributed to the locality of experience and the ability to decompose complex computations into smaller steps. The objective is formulated to accurately predict the remaining sequence rather than just the next token, which the authors find leads to a more effective loss for learning rationales. Quiet-STaR operates through three main steps. First, parallel rationale generation involves creating multiple rationale candidates for each token in the input sequence, marked by special tokens. Second, a mixing head is trained to determine how much the post-rationale predictions should influence the final output, helping to smooth the transition during fine-tuning. Third, rationale generation parameters are optimized using reinforce and teacher forcing techniques to improve future token predictions and reduce variance. This iterative process enhances the model's ability to generate useful rationales. Figure 3 illustrates the process of parallel generation in which an attention mask is constructed to enable all thought tokens to focus on themselves, preceding thought tokens within the same thought, and the preceding text. This setup facilitates the generation of continuations for all thoughts simultaneously. Each inference call is utilized to produce one additional thought token for all text tokens. This parallelized approach is made efficient by caching each forward pass and concatenating a diagonal attention mask to the previous attention mask, allowing each generated token to attend to all tokens used to generate it, including itself. Figure 4 illustrates the forward pass and teacher forcing mechanism in our algorithm. Solid lines represent the language model's computation, while dashed lines indicate tokens inserted via teacher forcing. The mixer or mixing head determines the extent to which post-thought prediction logits are used. The figure specifically visualizes predicting 3 tokens ahead, with thought generation details provided in Figure 1 and Figure 3. The experiments were designed to test whether Quiet-STaR improves the prediction of tokens that require reasoning. The base model used was Mistral 7b, and the datasets included OpenWebMath and C4. The primary objective was to predict tokens that necessitate reasoning. In terms of downstream performance, Quiet-STaR showed a 10.9% improvement on Common Sense QA and a 5% improvement on GSM-8K. These improvements were found to scale with the length of the rationales generated during training. Regarding the distribution of improvements, it was observed that there was minimal improvement on arbitrary tokens, but a disproportionate improvement on more difficult tokens, particularly those requiring the recall of relevant information. Figure 5 illustrates the zero-shot performance of the Quiet-STaR applied to chain of thought on GSM-8K. The figure visualizes how employing a Quiet-STaR trained Mistral model enhances chain of thought performance. Specifically, an 8-thought token trained model is utilized, and its internal thoughts are leveraged to improve the tokens in a zero-shot chain of thought scenario, as described by Kojima et al., 2022. The proposed framework introduces simplifications to address meta-learning challenges. It is noted that the techniques have only been applied to a 7 billion parameter model, and it is hypothesized that applying these techniques to a better model would yield significantly better results. The framework results in substantial overhead, generating many tokens before each additional token, which can also be seen as an advantage as it allows leveraging additional compute to enhance next token prediction. However, the current implementation does not support dynamically predicting when to generate or end a rationale. Future extensions could include dynamically predicting the rationale and applying a threshold to prevent generating thoughts that would not be incorporated, although this is expected to be a more difficult task. Quiet-STaR represents a significant advancement in language models, demonstrating improvements in downstream reasoning tasks and the generation of meaningful rationales. This approach suggests a path towards more robust and adaptable models. Looking ahead, future research could explore methods to ensemble thoughts to enhance prediction accuracy and dynamically allocate computational resources based on the model's needs. However, it is crucial to address ethical concerns, such as ensuring the faithfulness of the model's reasoning and mitigating the risk of harmful or biased patterns. The use of datasets with known biases, like common sense QA, also raises questions about the ethical implications of such research. Thank you for watching.